Okay, thank you. So yes, today we have the last lecture, and um, I have been talking about dark matter so far, and we saw some details. It was not for no reason, because basically whatever I'm going to tell you today about bias tracer and energy space is going to build on what we did so far. And of course, it wouldn't be. Some of you asked me yesterday, does this work really only for dark matter, or actually it is more general? And of course, I wouldn't be giving this course if it was only about dark matter, because this is, of course, maybe interesting academically to find some way to compute a pure dark matter, something in the pure dark matter scenarios. But in the real universe, we're observing galaxies, we're observing them in redshift space, and so therefore we're really interested in some theoretical methods that can be applicable to this much more general case. Okay. So it turns out, of course, that all the main points that we made about dark matter are equally applicable also to this more general case. So it is not only about dark matter, it is about galaxies, and you can use the same logic. So the two basic things that we are going to use is that on very large scales, even the galaxy density field itself can be described as a fluid-like. It has a fluid-like behavior where the main expansion parameter is the small variance of the density field. This will still be the case. The same way, following this EFT logic as for the dark matter, we have to make sure to consistently take into account all small-scale impact that can propagate on large scales. This is the thing number 2. So we will have to be careful about what kind of free coefficients and what kind of free momentum-dependent templates do we have in our final answer. And the number 3 is the same as for the dark matter. There will be still large bulk flows, which have to be taken into account through these infrared summations. So all the aspects that we discussed so far will generalize pretty straightforwardly also for the case of galaxies and for the case of redshift space. And so the reason why this is expected to work is because these EFT methods are very general. We never even have to know that galaxies exist or what are they made of. In the same way as when people were doing fluid dynamics, they didn't know that atoms or molecules exist. They had no idea about that. For them, fluid was a continuous medium. Nevertheless, as often is the case in physics, the low energy theory, let's say when we talk about more theoretical or particle physics, or when we talk about some real world condensed matter systems, like a long distance behavior of a system, so long run fluctuations, have some universal behavior very often, which doesn't depend on any microscopic details. And in the same way as we discussed dark matter, we can talk about galaxies, we can talk about anything you want. The main features will be the same. And so the general really thing that we always do in these CFTs is to simply identify what are the relevant degrees of freedom that we want to describe. In this case, this is the density contrast for galaxies, let's say. Then we have to identify all relevant symmetries, and I will say a little bit about that. You remember for dark matter, these symmetries were the trivial ones, like there was a rotational invariance in space, translational invariance. We had the invariance in the Galileo transformations, which will give us this particular derivative structure in the fluid equations, time derivatives followed by, basically replaced by this like convective derivative where you have to take also velocities and gradient with respect to x into account. And then we had the equivalence principle. We were saying that things can depend only on the two derivatives of gravitational potential and not on the gravitational potential itself, for example, and so on. So, and finally, we always have to have in mind some expansion parameter in these EFTs. Typically, this will be some small density fluctuation, and I told you there is a derivative expansion. So you can also, in principle, have multiple expansion parameters, and here we have the derivative expansion and expansion in terms of the fields. And once we identify the relevant degrees of freedom or relevant symmetries and expansion parameters, we can, in principle, order by order in perturbation theory, write down all equations of motion. Okay. So the way we derived fluid-like equations for dark matter, or we didn't derive them, but I sketched the derivation, was to start from the full exact equation, which was the Boltzmann, collisionless Boltzmann equation, or Vlasov equation. And then we did this smoothing. As a consequence of the smoothing, we had some effective stress tensor, and then equations of motion were what I showed yesterday. But however, we didn't have to do that. We could just say, like, okay, we want to describe, we don't even know what dark matter is, or what is it made of, or what is its exact equation of motion. All that we know is that on large scales, the relevant degrees of freedom are such and such. These are the relevant symmetries. Gravitational force is the only relevant force. And these are the parameters. And basically, if you start with the generic assumptions like that, you can see that you're forced to write the same equations of motion that I showed yesterday. So simply, these symmetries are constraining enough to tell you what do you have to write down. And one example, maybe to keep in mind, is that even though this Vlasov equation is correct for the collisionless system, where we are imagining the dark matter particles are really some particles that interact only gravitationally, you can have a different dark matter microscopic theories. For example, I guess that Mustafa mentioned this ultralight dark matter. This is one other option where you don't really have individual particles, but you have something like collective coherent oscillations of the axion field. And in that case, you can show that on large scales, you can rewrite the Schrödinger equation which describes the system in a way which resembles a lot of the fluid description with some additional quantum pressure, the so-called quantum pressure term, which can be made very small if the mass of the axion is large. So for practical purposes, in some sense, on large scales, you can get a perfect fluid description starting from this ultralight axion microphysical theory. However, if you still focus only on the long wavelength density fluctuations in this different dark matter scenario, you will find the same equations of motion as for the collisionless dark matter, which is made of particles. So you see, even though the microphysics can be different, and if you zoom in and look inside the dark matter halos, the dark matter can behave very differently. On large scales, it is forced to always behave in a universal way. And this is this power of the EFT. The only difference between these two EFT descriptions can be that these coefficients, these three parameters that I was talking about yesterday, can be slightly different. In the same way as different fluids have the same fluid equations, but their viscosity can be different. This is the only thing that can differ, okay? Now, it will turn out that the same is true for galaxies. I'm not going to do this, but you can sit down and ask what are the degrees of freedom, what are the symmetries, and write down the full equations of motion and solve them perturbatively. We're not going to do that, but let us just briefly discuss this because it will be relevant. So first of all, what are the relevant degrees of freedom? Well, this is easy. Here we're talking about delta G of x and t, maybe let me call it tau, which by definition is very similar to the dark matter density contrast. It's just a raw galaxy this time, minus raw galaxy bar, some mean galaxy density divided by the mean galaxy density, okay? So you should imagine that in your survey, you have a bunch of galaxies, you find some mean galaxy density, and you compute density contrast in this way. So this is our field, and we want to basically find we want to find how this field relates to the initial conditions, given some cosmological model with some cosmological parameters, and then we want to compute, for example, some observable, like the power spectrum of this field or the bispectrum of this field, and so on. Now, what are the relevant symmetries? Okay, so there are trivial symmetries, like there will be some rotational invariance or translational invariance. Actually, not so trivial. Let me maybe say in what sense. So, but most importantly, compared to the dark matter case, we have to give up mass and momentum conservation. So let me explain this, And we will see this in a specific calculation why this is the case. So it is not that galaxy formation violates mass conservation. This is not what happens. Of course, if you run an n-body simulation and galaxy forms, the mass will be conserved. However, what actually is lost, it is lost in the observations in the following sense. Imagine you have a dark matter halo, which has a lot of dark matter particles, and there is another dark matter halo, which has a few particles. Okay. Now there is a galaxy which lives inside. Okay. There's a galaxy here, and there is perhaps a little bit smaller galaxy here. And an observer who is observing this universe will just assign one point. When we look at the galaxy surveys, we don't know what is the mass of the host dark matter halo. We basically cannot tell if this is 2 times more massive than this one. In observations, they all count the same. So we're just counting as dots, like dot, 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 dot. So we're just counting how many galaxies there are of a certain type in a given region of space. And this is how we make our catalogs. So in other words, these 2 galaxies count the same. But of course, they do not have the same mass, including the host dark matter halo. So simply by not knowing what is the dark matter halo mass, we are expecting that the density field of galaxies will not respect mass and therefore momentum conservation. Okay, so it is in this sense that this will be lost. And there were several important properties, for example, of the perturbation theory kernels and so on, that were depending on mass and momentum conservation, and this will be gone now for galaxies. Okay, this will not be there. Is it clear in what sense the way we observe things and make this map effectively violates mass and momentum conservation? Because we just don't know the mass. We count everybody to be the same, like 1. Okay. Okay, so this is one important thing that we have to give up. And the equations of motion for dark matter didn't have many free parameters simply because some of the symmetries were fixing a lot of coefficients in the equations of motion. They were not allowing them to be different. Now here, of course, things will be very different. We're going to end up having many more free parameters simply because we are giving up one of the most important symmetries. The second thing is that in the redshift space, there is a preferred line of sight. So we are observing things along a given line of sight, and because I'm going to discuss this in a moment in more detail. But since we have some preferred line of sight, then we will lose isotropy. So things are going to, in real world, be a bit more complicated. When we talk about realistic galaxy density field, let's say that you're observing along a given line of sight. I'm going to explain in a moment what does it mean we lose isotropy. We lose isotropy because the way we measure, the way we make galaxy maps to do any of these analyses in the real world is to convert their redshifts to distances. But this conversion depends on their local velocities. And in particular, because there is a little bit of peculiar velocity contributing to the redshift, and in particular, there is a projection of these peculiar velocities along the line of sight. So for example, if you have 2 galaxies at the same physical distance, but they're moving in opposite directions, one of them will appear to be closer to you, another one will appear to be further away from you, simply because you're converting redshifts to distances. And we don't know the real distance to the galaxies. And so this is what is called the redshift space distortions. And because there is a preferred line of sight on which you project peculiar velocities, then you're going to end up with some preferred direction in your map, in your 2-point function or 3-point or whatever n-point function. And this is going to mean, this will mean that basically you're losing isotropy. Okay. So One important thing is, however, is that the equivalence principle still holds. This actually is very important because some of the things that we discussed about dark matter, for example, that the stress tensor cannot depend on the gravitational potential itself, but on the derivatives of the gravitational potential, the real tidal fields and real forces. This was true because of the equivalence principle. You cannot measure the gravitational potential. You can only measure two derivatives of the gravitational potential. Even the first derivative of the gravitational potential is acceleration. So you may say, well, but we can see that there is an acceleration. So it is true if there is some floor to keep me from falling down to the earth, but if I'm in a free-falling reference frame, I'm not sensitive to the homogeneous gravitational acceleration, so which is the first derivative of the gravitational potential. So I can measure only tidal forces, and this will remain true also for galaxies. The galaxies can experience, they're bound to obey the equivalence principle, so they have to behave in a free-falling, when they freely falling in the background of some long wavelength fluctuations, they have to behave the same way as dark matter. And this, of course, will be important because this infrared resumation that I was telling you about yesterday for dark matter, where we were basically calculating what is the displacement the dark matter particles do, it was large, and there was some way to resum it and to include it non-perturbatively, take it non-perturbatively into account, would be the same for galaxies. So galaxies will have the same infrared resumation, and you don't have to worry about how does it work there, because no matter what are the astrophysical processes that are happening inside the galaxy, everything has to be like moving the same way as dark matter in the external gravitational field, okay, because of the equivalence principle. And similarly, the only things that that locally galaxy formation can depend on are tidal fields of the long wavelength modes. So no gravitational potential itself, or just the gradient of gravitational potential. Okay, so is this clear? And finally, the expansion parameters are going to be the same as for dark matter. So we already discussed them. I will not repeat the story here. Okay, so in principle, once we identify this, you see, like when you lose symmetries, things become more complicated. So now if you wanted to write down equations of motion, which do not have isotropy, and then there is no mass momentum conservation, and so on and so forth, this will be much more complicated, and we could do it in principle. It will take a lot of time to make sure that you're not missing any terms and to fix all the coefficients and so on. But luckily, there is a simpler way, and historically, this is how people used to do things. There is a simpler way, which is we don't want to really write down the equations of motion for galaxies, but what we want to do is to use the fact that we already found some nonlinear solution for the dark matter, and basically ask ourselves how the galaxy density field is related to this nonlinear dark matter field. There is a simpler way to avoid, basically, if you want, doing everything from scratch, even though you can do that. There is this simpler way, which you will always find in practice, and historically, this is how people thought about it. And here now, we basically want to ask, okay, so what is the most general expression that we can write down following these assumptions that I just mentioned in the previous slide, such that we can relate what the galaxies do in terms of what dark matter does. So you can imagine that. So again, here the logic is that, of course, galaxy formation is a very complicated thing, and we don't know how does it work. So you can run some simulation, but there you have to put as an input some things that you're not sure about. For example, how many supernovae explode, what is the formation rate, do you have a strong or not so strong AGN feedback, I don't know, how fast or slow like your gas cools or heats up, and things like this. So we don't have some particular equations to solve. We don't have exact theory of galaxy formation. So we put many things by hand, and there are some simple prescriptions which are more or less motivated based on some observations and so on. So in principle, this galaxy formation is a very complicated process, but it depends on all kinds of things. For example, if you change even the craziest thing, like electron mass a little bit, you will change how the galaxies look like, because or you change some parameters of the nuclear reactions, you will change completely how the galaxy looks like, because star formation will be very different, and stellar evolution will be different, and like, you know, how the universe appears to us is such a non-trivial and complicated function of all these details that sometimes we even think it's hopeless to know all these details. However, what is important is, again, when we look, this is true. So these complications are always there if you want to have the exact microphysics description. If you want to talk only about the long wavelength density fields, then things will considerably simplify, because all these details about how galaxies form and what is the electron mass and, like, I don't know, like how strong are nuclear reactions and so on and so forth, these are some kind of a local details which determine some local physics. But the long wavelength density fields can basically, in the full function for what galaxies are, galaxy density field is, apart from these local things, the only things that have some long wavelength component and can vary from one place to another are the long wavelength dark matter fields. So basically, all that we want to do is to write down the galaxy density field as a function of some underlying dark matter field with some free coefficients which encode all small-scale physics that is happening. We don't know these coefficients. To compute them, we would have to have the microphysical description of galaxy formation, which we don't. In the same way as for the stress tensor the other day, there were some free parameters that we didn't know, which encode really the small-scale physics of dark matter that we don't know. So here, it's a bit more general. We want to encode in these coefficients the small-scale galaxy formation physics that we don't know. And so, in principle, like this framework is general enough. And now let me write down one expression. One important point here, though, is that, and this is something that I didn't comment when we were talking about dark matter, so let me comment here, is that you have to be a bit careful about how do you write this formula. So naively, you may think that, well, if I want to, so what you're saying is that, well, there is some complicated function of all possible things, like, I don't know, like electron mass or like nuclear reactions, and I don't know, supernova explosion rate, and so on and so forth. And then also some environment, long wavelength over densities, like tidal fields, and so on and so forth. So I can take this complicated function, I can expand. You see, for example, the nuclear reactions do not depend on space. They're the same everywhere. The electron mass is the same everywhere. So I can take only things that depend on space, which are basically, let's say, the density fields in the universe, expand perturbatively this big function in these density fields, and I'm going to end up with some complicated coefficients times usual density field delta, some higher order propagation theory, and so on. So you may naively think that I can do this expansion locally in space. I can just take, let's say, current moment of time, and I say my galaxy density field is some Taylor expansion with unknown coefficients in terms of the underlying dark matter field. This is not entirely true, and the reason for that is that one thing that we didn't discuss so far, but now it's time to talk about it, is that so you can do these kind of things only if the evolution of fluctuations is relatively fast. So you can have, in a sense, a local in time expansion of this type only if the evolution of fluctuations is sufficiently fast. Okay, so in some sense, in the same way, for example, what allows us to do this effective theory is the separation of scales in space. So there is some spatial scales where things are very complicated, and then if we stay on large scales, things become much simpler. Now here, the same thing should in principle happen in time if you want to have this simple local in time behavior. That for example, you would ideally want for small scale fluctuations to evolve fast, and they don't have some kind of a long-term memory, and the long wavelength fluctuations can evolve slowly, and then you have a complete separation both in space and time. So you can do local in time expansion, and you can do some local physics in space, where you can separate scales in both directions. And indeed, in the relativistic quantum field theories, this is exactly what happens. Like if you're considering small scales, this also means short times. There is like one-to-one correspondence. However, in cosmology, this is not a relativistic theory, and here things are a little bit different. And one thing that actually happens is that the characteristic time scale for all fluctuations is approximately, well, h to the minus 1. So both long wavelength density fields and short wavelength density fields evolve with a similar time scale. So there is no separation in time. There are no fast and slow Fourier modes. They're all evolving in a similar time scale. For example, if you imagine some, let's say it takes age of the universe for the dark matter halos to form. So it's not some fast process, okay? Maybe a little bit less, but there is not like some big parametric separation compared to, for example, how the fluctuations evolve on largest possible scales. And because we have this mixing, so because we have this feature that things are evolving slowly, this means that when you talk about the expansion of the long wavelength field, let's say for galaxies, but even for dark matter, even though we were a bit sloppy, so we were not discussing this so far. But if you talk about galaxies, so the galaxies will not depend in some region of space only on what are the current, like what is the current distribution of matter, of dark matter and other long wavelength fields, but it can also depend because it has some like this slow evolution of short scales has some memory. It also depends on how the things were involved to get to that point. Okay, and so most generally, this is why what we have to write down is that our model for galaxies distributed in some space and time at the moment is going to be something like that. We started some initial time up to now. And now what we want to write down is some more general functions, so non-local in time, basically, where we want to have some free coefficients, which we don't know what they are. They depend on the microphysics. But there's some kernels which have some non-trivial dependence on the current time and this t prime under the integral. And then there is an expansion in the dark matter density field. But since as the time goes on and you're integrating from the initial time, the position of this dark matter density field, you have to keep track of it and follow the fluid element along its word line. So for example, the simplest term, the only term at, let's say, leading order in perturbation theory that you can write down. So what, delta G is a scalar. So what can it depend on if I allow you only one power of fluctuation? Well, the only thing that can depend on is the overdensity of dark matter and nothing else. At leading order in perturbation theory, in linear theory, like this delta G can depend on locally only on delta matter, and all other non-trivial things are encoded on small scales are encoded in this coefficient here, which we don't know. Now, if you go to higher orders in perturbation theory, then you can write more terms. For example, at second order in perturbation theory, I can write two possible terms. I can write delta squared, right? This is like 2 powers of the fields. Let me suppress here this explicit time dependence because it will be too complicated, too cumbersome. So let me just write something like that, delta nonlinear square. But there is another second order term that we can write down, which is, I'm going to call it tide. And then here we have di, dj phi square. So you see, these two terms are basically the same order in perturbation theory. Let me remind you that delta is Laplacian of phi. So it has two derivatives on phi and then squared. Here is like a different index structure, which at linear order we cannot write down because this object doesn't have any indices. We have to contract this with delta ij. This is why this is the only option. But at second order, we can have a tidal field squared. This is another thing that galaxies can depend on, and so on. So you can now go on at higher and higher orders in perturbation theory and write all possible terms that you want. So of course, you can also do the expansion in derivatives. So for example, you can start adding terms like that. So this term, for example, is the leading order in perturbation theory, but it has it is higher order in derivative expansion. In principle, to make this C dimensionless, I can divide by the K nonlinear square. So this is also an option, and so on and so forth. Okay. So this is the most general way in which the delta galaxy can depend on the underlying matter fluctuations, and all other dependencies on that, how stars form and so on and so forth, is encoded in these free coefficients. So now you see we have a bunch of free coefficients, which we don't know. We have to fit them from the data together with other cosmological parameters. But what is nice is that we have some systematic way to relate the underlying nonlinear dark matter field with the galaxy density field. Okay, so we don't have to find out what are the equations of motion for galaxies. We don't have to find out the whole thing that I was talking about before. Using this formula, we can use whatever we found for the dark matter to build up the galaxy density field in this way. Okay. Now, this formula is still not very useful. It is not very useful because it is so complicated. You see, you have this non-local in time behavior and these kernels, which are non-trivial functions of two variables, a very complicated system. But again, using perturbation theory can be simplified. So first of all, let me make a little cartoon. So this is some initial x, initial time. This is final time and final position. And we're imagining that galaxy follows basically this line, and at the beginning is just a bunch of dark matter particles, and eventually at some point a galaxy forms where we see it today. And as I said, it is sensitive to the entire evolution inside this region as the whole region maybe moves in space and evolves in time. And we have to follow this dependence on the local dark matter density and tidal fields and so on along this world line. This is what this integral tells you. And in principle, of course, things are very complicated, but what you can do is to then basically do the expansion of, let's say, let me do an example following the fluid element of delta, for example. We can write this as delta nonlinear in a position x, which is the final position, plus, and then we can do the Taylor expansion in time. These details are really not important. I'm just writing it down for completeness of delta nonlinear x and so on. Well, where this derivative must be convective derivative. And when you do this for all these fields, you will see that you can then use the equations of motion, perturbation theory equations of motion for the nonlinear dark matter, to basically reorganize all this expansion in a way that you're going to get something which is effectively local in time, but it may be non-local in space because in higher orders in perturbation theory, this will be the case because you have these velocities, which will have like 1 over Laplacian at some point and so on and so forth. So you can reorganize this term in a way which is a bit simpler to use in practice, where basically you can expand all these fields take their time dependence perturbatively, then use the equations of motion for dark matter to find all these time derivatives, plug everything back, and you will get like a bunch of terms that will appear like at a given order in perturbation theory with some complicated time dependence, which now you can collapse into a single coefficient evaluated at the late time. I'm not going to show all these details. You can take a look in the literature. But in practice, at leading orders in perturbation theory, what this allows you to do is to rewrite this complicated expression in a much simpler way that I'm sure you have seen before. And this is just a simple bias expansion. So you will say that perhaps the galaxy density field model depends on some bias coefficient B1, which depends on time, times the nonlinear dark matter evaluated at x and tau. Then you can have, for example, the second order bias term, where you have delta nonlinear square minus expectation divided by delta nonlinear square. You may have this tidal bias. I'm going to use the term which I'm going to define to be the operator G, G2, and so on. For example, the non-local term will look like that, and so on. So manipulating, like expanding distance perturbatively, you can write down the model, which at leading orders in perturbation theory looks like a local in time and local in space. At higher orders in perturbation theory, you will have some terms which have some more complicated structure. But at least for the one loop power spectrum calculations, you don't have to worry about those. So this is the usual, I think, bias expansion that you have seen probably in the literature. Okay. And again, now, like we wrote the galaxy density field as a function of basically dark matter, and it's like tidal field and so on. And there is a bunch of free parameters which we don't know, and they will depend. If you change the galaxy sample, you will have different bias parameters. If you change how galaxies form, you will have different bias parameters. If you, I don't know, change cosmology, you will have different bias parameters. And we don't know these functions a priori, but we can measure them in the data. Okay, now I would like to comment on the fact that, like, for example, let us ask ourselves how delta G model depends on the linear density field. Okay, maybe let me write it like that just to be consistent. So what is the function in terms of, so here it is written in terms of the nonlinear field, but let us write down in terms of the linear fields. And so this is very easy. You just have to remember, for example, that the nonlinear matter field was basically the linear field plus some second order field and so on. This second order field was some complicated convolution where you had F2 and two linear fields. I hope that you remember this, and so on and so forth. So for example, if you want to stay at second order, we are going to have one second order nonlinear contribution from here, which is this one. And then, for example, these are already squared. So here we only have to take linear fields and square them. And so this thing, let's say at leading order in perturbation theory, is just B1 times delta linear. Okay, this is the only linear term. But then when we go to second order, we are going to have something like that. So there will be F2 coming from here. Let me say that I'm going to be very sloppy in principle. Now it depends, how do you want to, I'm trying to write this in momentum space. Let me maybe just do it, okay? It will take some time, but let me be very precise. So in momentum space, this is going to be something like that. There will be B1 times delta of K, the linear field. And then we are going to have some complicated kernel, which I'm going to call, let's say, X kernel or Y kernel. So there will be like integrals over Q1 and Q2 as before. You may have some complicated perturbation theory kernel, which is not the same as F2 before. So let's call it Y2, which depends on Q1 and Q2 and bias parameters. And then we're going to have two linear fields convolved. So remember, if this Y2 is equal to F2, this is only the second order perturbation theory result. But now we have some additional terms. Here, there's an additional term here. So what is this Y2 going to look like? Well, first of all, it will have B1 multiplying F2. So B1 times F2, which depends on Q1 and Q2. And then you're going to have like this term here, which is B2 over 2. And then there will be another term coming from here, which is Q1 dot Q2 squared over Q1 squared minus 1. When you go to Fourier space, these derivatives and phi, right, in terms of delta, you remember phi is like basically 1 over Laplacian times delta. So you're really going to get this momentum structure. So you see that for galaxies, the second order perturbation theory kernel is not just F2, but also it has additional terms. And this has an important consequence. So you remember that I was telling you that F2, when you're considering some particular momentum configuration, for example, Q and K minus Q, and then you send Q to be much larger than K, this used to go like K squared over Q squared. And this was due to the mass and momentum conservation. However, if you look at galaxies and you do the same exercise, because now you introduce some other, so if there was only F2, that would still be the case. But since you have these new numbers appearing here, they're going to spoil this property, and this is going to go like a constant. Okay? So this means, this is what I said at the beginning, that somehow when we talk about the galaxy density field, we don't expect to have some effective mass and momentum conservation. Of course, fundamentally, mass and momentum are conserved, but just the very fact that we are just counting dots without knowing whether they are in a very massive dark matter halo or a very small mass dark matter halo will effectively lead to the loss of mass and momentum conservation. And you can see it even in perturbation theory results. So these new additional free coefficients are basically going away from these behaviors we have in the past for dark matter. Okay, so I'm already running out of time. So let me say one more important thing about this galaxy density field. So far, I was just telling you about the model part, if you want, or the deterministic part somehow, which depends on the underlying distribution of dark matter. The full galaxy density field is what we wrote so far, plus some noise. And this noise is basically coming from the fact that we don't have a continuous field of galaxies. The galaxies are sparse. And so we are basically always having some representation of some true underlying galaxy density field, which is made with a finite number of particles. So this is like, for this reason, this is called the shot noise or the sampling noise or Poisson noise if the process is purely Poissonian. And so this noise is something that is always there. And of course, if you have more galaxies, if the number density of galaxies is larger, then the noise will go down because you're sampling your underlying galaxy density field better. If you have fewer galaxies, the noise will go up because you are sampling your field with the fewer particles. And Matthias already mentioned this in the context of gravitational waves in the first lecture, if you remember. There, the similar thing happens. And so this noise is like at leading order. You can think of it as a simple Poisson noise, and you know that the power spectrum of this noise is basically constant. So, so the full galaxy density field then is going to be described by this part that correlates or depends on the long wavelength matter density fields and some random stochastic noise, which comes from the fact that we have a finite number of galaxies to sample the density field. The power spectrum of delta G we can compute using perturbation theory, order by order perturbation theory, and the power spectrum of this noise at leading order is just a constant. Okay. Are there any questions about this? Yes. Yeah. No, sorry. This is like the delta G as a function of the initial conditions. I want to write it as a function of the initial conditions. So it has a part which is linear in the initial conditions, and then, oh, sorry, there is a typo. So there is like, and there is a part which is quadratic in the initial conditions. Then there will be a part which is cubic in the initial conditions, and so on and so forth. I'm just doing the expansion because if you remember, the dark matter density field, the way we solved the equations, nonlinear equations, was that we wrote the nonlinear solution as some convolutions of the initial density fields. So here I'm trying to do the same. I'm trying to say, like, if I know how delta G depends on the nonlinear dark matter, and I know how the nonlinear matter depends on the initial density field, I can then write down how the galaxy density field depends on the initial conditions. Okay, this dependence this time is more complicated because it has more free parameters. Because this like for the reasons we discussed. There was another question. Well, I just first of all, I told you that when we make a galaxy, let's say catalog, we never specify what is the mass of the under. I mean, we can do it in simulation, of course, but in the real data, it's very hard to estimate what is the mass of the host halo. So we are counting galaxies as dots. So they all have the same mass for us. Let's say the mass 1. Okay, they're just the bright dots which sit in. So basically, we effectively. When you ask me, like, what is the mass of this region of space, I will just count the dots and tell you the number. But this may nothing to do with reality because I'm like forgetting about dark matter, or I don't have a correct estimate of what is the underlying mass. So the density field of galaxies should not obey mass and momentum conservation because it is not constructed keeping in mind mass and momentum conservation. So now this is like intuitively why these two things are not there. And I just wanted to show here explicitly in the equations for this galaxy density field that this is really what is happening. So you remember that this property of the perturbation theory kernels, where you have, so what is this? So basically here you have two Fourier modes which have very high momentum, which combine to give you one long wavelength fluctuation. And so this is a configuration in which we have a short scales combining to give you a long wavelength field. Or in other words, this is the situation in which we're asking, how can the small scale fluctuations impact the long wavelength density fluctuations? And we were saying because the mass momentum is conserved, there was a general argument that this must scale a k square. And indeed, if you explicitly check this limit in the F2 kernel, you will indeed find that it scales at k square over q square because the dark matter equations of motion conserve mass moment. Now, for galaxies, there is no such thing because the way that the field is constructed. And therefore, if you look at the same thing, if you ask, how can the small scale fluctuations impact the galaxy density field on large scales? Well, they can impact it a lot. There is no this k square suppression. This goes like a constant. And indeed, you can compute that this constant, I think, is exactly B2 over 2. Okay, so this is the way that we basically go from dark matter to galaxies. And now let me, so I should stop at 10:30. Is that correct? Yeah, okay. So let me very, very, very briefly maybe also tell you about redshift space distortions and how do we include redshift space distortions in the whole story. So I already told you that when we observe, so let's talk about RSD, which is redshift space distortions. So these are distortions when we observe things in redshift space. What does it mean to observe things in redshift space? Well, like there is an observer sitting here. There is a galaxy along this line of sight N. And now we want to build some maps of the universe. We want to make some kind of a catalog and tell the position of the sky, like, you know, or build some 3D kind of representation of the map of the universe. And so of course, we know the angular position of the galaxy very well, but then the question is like, what is its distance, okay? And so the only way that we know how to measure distances in cosmology is to convert redshift to distance, okay? And if all galaxies had like 0 peculiar velocity, then this would be a very good way to make maps because we would just use the usual, basically there will be no mistake because we would just convert the exact redshift, which corresponds to a given distance, and there will be no problem. However, galaxies have some, on top of the Hubble flow, they have some peculiar velocities. They're moving in the clusters, they're falling towards the center of some bigger structure, and so on and so forth. So these peculiar velocities also contribute to the redshift. So when we are measuring a redshift of the galaxy, it has 2 components. There is a redshift from like the usual expansion of the universe, plus there is a bit of a contribution from the peculiar velocities. However, we don't know what is the peculiar velocity of each individual galaxy. We just measure the total sum, and we convert the total redshift to a fixed distance, okay? And when we do this, we inevitably introduce some distortions in the map because there is some leakage of these peculiar velocities in the positions of the galaxies as we reconstruct them, okay? So this is what is called redshift space distortions. And the position in redshift space is going to be the same as the position in real space. Of course, the angular position is always the same, but then around the radial direction, you introduce some distortion which depends on velocity. So basically, it is given by the peculiar velocity of a galaxy projected along the line of sight times the line of sight itself. So you see, if, for example, a galaxy is moving at a fixed redshift towards you, you will see that the redshift is a bit smaller because there's a little bit of a blue shift because of the peculiar velocity. So you will put it to a distance closer to you. And if there's a galaxy moving at the same point away from you, it will look a bit more red. There will be more redshift because of the peculiar velocity. So you will put it a little bit further away from you. So even if you start with a spherical distribution of galaxies, which are in some cluster, this will get elongated in your map because you will tend to put further away those that are moving away from you and closer those that are moving towards you. And this elongation of, let's say, clusters is called the fingers of God, for example. You have maybe heard about that. So the fingers of God are these structures in the maps of galaxy energy space, which are very elongated, and they come from this effect that when you have, let's say, some random velocities in a cluster, you will randomly push somebody very far away, somebody closer to you, so you will make this elongated structure because of converting to the redshift. Okay? So now, on small scales, we cannot predict any of these velocities, of course. On large scales, in perturbation theory, we can also solve for the velocity of the galaxies or dark matter particles in the same way that we solve for delta. And then again, we can make this map from real to Redshift space perturbatively. I'm not going to give you any details, but let me maybe just say what is the underlying logic. So the logic is that since I have this change of coordinates from x to s, to Redshift space coordinates, but the number of galaxies is preserved when I do this mapping, whatever it is. So I can write down something like that. That 1 plus delta galaxies in Redshift space, which is labeled by s, which depends on these coordinates s, and then d3s. So the total density of galaxies in some volume is preserved by this mapping. And so this is equal to 1 plus delta g of x d3x. And so now you see that if you know this Jacobian of this mapping, and you know it, this Jacobian will depend on the velocities. If you know the Jacobian and you know the distribution of galaxies in real space, you can compute what is the distribution of galaxies in Redshift space. So the distribution of galaxies in Redshift space will be the same as the real space plus corrections coming from this Jacobian, which depend on velocity. So you're going to introduce a lot of new nonlinear terms where you have multiplications of densities and velocities, velocity square, and so on and so forth. But all of these things can be computed again order by order in perturbation theory. There is nothing now conceptually difficult about doing that. You have to be careful to again renormalize everything, take into account, add all the possible counter terms that you need to absorb all the UV dependence in these maps and so on and so forth. But like, you can just do this. There is not real new ingredient. And then like basically you can find, so what you have to do is to compute ds by dx and then find delta g in terms of delta g of x and things like delta g of x times velocities and so on. There will be a bunch of new terms, and of course all of these terms can be computed in perturbation theory. So I will not give you any more details because we are running out of time, but for instance, again, in linear theory, just to make some connection with what you probably know. So in linear theory, this delta s g of k, let's say, you do it in Fourier space, is equal to b1 plus f mu squared times delta matter, basically the linear field. Okay. Where this mu is defined as the cosine of the angle between the line of sight and the wave number k. And this is nothing but the Kaiser formula. You have already probably seen that in your courses in cosmology. So in the B1 term, of course, is just delta G. But then this correction, which depends on the line of sight, and you see introduces some anisotropy, is what comes out from this mapping between real and Redshift space. And it's basically the first term, which is linear in velocity. So basically, the velocity term gives you this contribution. And you can find then similarly how expressions look like at higher orders in perturbation theory again. Okay, you can again perturbatively compute like all higher orders. So if you now compute the linear PG GS linear of K, this of course is a well-known formula, which is just the square of this times P linear of K. Okay, so you can see that. Sorry, let me maybe be a bit more specific here. What I want to say is that this really depends on K, magnitude of K and the angle mu. So we lost isotropy. It's not that everything is just fully isotropic, but there is some dependence on like, because you have a preferred line of sight, there is a dependence on this angle between like the line of sight and Fourier modes k that you're considering. And so this means that the two-point function, the power spectrum in redshift space, is not isotropic. That, of course, is well known. And people sometimes do the multiple expansion of this anisotropic power spectrum, and they defined power spectrum multiples, which depend only on k, which are defined to be, in the usual way, just the integrals of this galaxy anisotropic two-point function times Legendre polynomials P of mu. And for example, the monopole would be just the angular integral of this power spectrum. You can compute the quadrupole and hexadecapole and so on. And this is what people usually report when they talk about data. They will, for example, they do the galaxy survey. We're going to see it in a moment. They compute the power spectrum monopole, quadrupole, hexadecapole, and so on. They give you the spectra. And if you want to compare it to the theory, you have to compute the full anisotropic galaxy power spectrum with all the ingredients we discussed, compute these multiples, and then compare to the data. Are there any questions about this? Yes. Yes, so the conversion from distances, from redshift to distances depend on your cosmological model, because you have to assume some, let's say, angular distance, radial distance, whatever you have to, like some omega meter, Hubble, and so on and so forth. However, when people do this comparison to the data, okay, so basically the way it works is that you choose some fiducial cosmology, whatever this is, it's your choice. You do this conversion, and when you make theoretical predictions, you also do the same fiducial cosmology. You take it into account in a sense that you apply the same, whatever you will do in the data, you apply the same procedure in your theory, so that you make sure that the fiducial cosmology cancels. So there is a way to do it such that there is no dependence on the fiducial cosmology. Yes, in this particular step, there is this dependence, but you can also do the theoretical prediction by basically this Alcock-Paczynski rescaling of momenta, such that the dependence on the fiducial cosmology drops. And this is what is done in practice. Otherwise, it will be bad. Yeah. Okay, so I think that in the last 10 minutes, if I have time, I wanted to basically just show you how does this all work. So I was not very detailed today. I mean, like, I gave you some idea how to go from this for whatever we did for dark matter to galaxies and then to redshift space. And in principle, now you cannot read these slides because they're too small, but like it doesn't really matter. All that I want to say here is that if you want, for example, to compute the one loop power spectrum for galaxies in redshift space, there will be a finite number of ingredients, which is not so different at the end of the day for dark matter. And so the one loop expression will be the same as before. There will be linear theory, P22-like diagram, P13, plus this stochastic noise term, Poisson noise. And the only difference now is that these perturbation theory kernels that you're putting in this P22 or P13 are not F2 and F3, but they're slightly different. And now they also include, for example, these redshift space distortion nonlinearities and bias coefficients. Okay, but morally, the whole story is the same. The infrared resummation that we discussed yesterday is a bit more complicated because now you have a preferred direction on the line of sight, so you have to make sure to take this into account when you compute these bulk flows and how they broaden the BO peak. And at the end of the day, you end up with some theoretical model which has very well fixed momentum dependencies, a few free coefficients that you have to fit from the data, and you can just then check how well does it work. So the parameters in this model are cosmological parameters for whatever cosmology you want. And then there are some bias parameters. There are a few counter terms. So for the dark matter, there was only one. Here there will be more. and there is this shot noise. The amplitude of this Poisson noise is a priori unknown. So all these parameters are jointly fitted from the data, and then if you want to know only cosmology, you can simply marginalize over these nuisance parameters. Is this clear? Okay, so let's see how well does it work. So first of all, I want to say that you don't have to sit down and, I mean, you should probably go through this calculation a little bit, but you don't have to sit down and build the whole machinery by yourself. Now, there are a couple of like publicly available codes which are very simple to use. So if you want to compute any nonlinear observable, basically you can download any of them. I worked on one of those, but like all of them are fine, and they're going to give you basically anything that you want, like nonlinear dark matter, galaxies, galaxy matter, cross spectrum, really whatever you want. And they're very, very simple to use. They're basically some extension of the existing linear codes. So you can just plug in cosmological parameters. You can ask whatever cosmological model you want, and these codes will compute the full nonlinear data with at a time scale of order 1 second, okay? So they're very fast. They take basically equal time as the linear codes do. And this is very important because this is what, at the end of the day, allows, this is what Cora was talking about, that to do the MCMC analysis in reality. And now we have basically the infrastructure where we can really take the data, the galaxy clustering data, let's say, and analyze it in the same way as we do the cosmic microwave background. So the development of these codes in the past was crucial to do MCMC in CMB. And now we have a complete story where basically starting all the way from the initial conditions throughout the early universe, all the way to the late universe, we know how to do consistently computations, at least for the long wavelength degrees of freedom. And we have publicly available software where you can just play with and very quickly evaluate whatever you want, given the entire cosmological history. Okay. And so then, of course, it's very tempting to immediately go and use it in the data. Before that, let me just explain that, or tell you, or show to you how well does this theoretical model work. Because for dark matter, we had this check I showed you yesterday. How well does it fit the nonlinear dark matter field measured in simulations? So let's see how does this perturbation theory compare to, let's say, some simulations. And so here I'm showing, first of all, like the whole time we're talking about building the galaxy density field, so you don't even have to compute only the summary statistics of the power spectrum and compare to the simulation. You can also compare the maps directly. So what is shown here is some output of one of the well-known hydrodynamical simulations, Illustris TNG 300, for the neutral hydrogen. So this is like a hydrocode, so it is not some simple-minded like simulation. In principle, it should have at least some version of the full microphysics built in. And this is the output of a simulation for a given initial conditions. Then what you can do, in order not to have the cosmic variance, you can take the exact same initial conditions for Illustris and make the perturbation theory map, just using this formula that we derived this week. And look how well they agree. They're basically the same on large scales. They have all the features in the right places. If you compute the cross correlation between this map and that map, it will be very good to very, very high K, exactly as you expect in perturbation theory. The errors are going to be of the order of the two loops that you're neglecting, and so on and so forth. You can improve this calculation. So everything works basically as well as for the dark matter that I showed yesterday. Okay? And so this is a very rigorous test because we are not only fitting the power spectrum, we're making sure that basically all Fourier modes are kind of correct because we are reproducing the same density field as in the simulation. Not at all scales, of course. you can see that on small scales, they will disagree. Let's say at scales of a few megaparsec, there is no agreement anymore. But this is fine because perturbation theory is not supposed to work on small scales, only on large scales. So, however, I also want to emphasize, this is what I was saying the other day during the discussion, that these maps also have some noise. And this noise is like usually bigger than this difference of the disagreement. So for practical purposes, they are kind of the same, almost on all scales. If you want to take a look at the power spectrum, let me say that you can also do that. And this is now the same huge, gigantic simulation that I was talking about yesterday, where now, basically, originally, this big simulation was designed as a challenge for us to try to prove that our method works and that we recover the right cosmological parameters. So what happened is that Takahiro Nishimichi and Masahiro Takada prepared this giant simulation. They measured not the dark matter. What they did is to populate dark matter halos with, according to some HOD prescription, with some central galaxy satellite and so on, to resemble the BOSS data. Then they measured the power spectrum monopole and quadrupole. They gave this data to us and asked us to fit this data and try to recover cosmological parameters which were unknown to us. Okay, so the agreement was that whatever we give them, it goes on archive, whether it is wrong or correct. So it was a little bit of a bet, like whether we can do it or not. And the challenge was, of course, to do it in this huge volume, which is a very tiny error bars. So let me remind you again that here you don't even see the error bars because they're so small, and so the residuals are less than 1% in all these k-beams, for example, in the model. It's a super precise data. And so, like, as you can see here, these are our best fits. Like, all these ingredients we were discussing were crucial to get all these wiggles right in the power spectrum monopole and quadrupole. And on the right-hand side, you can see these posteriors, and you can focus, for example, on the green curve. So even if you go to k max of 0.16, you basically find unbiased cosmological parameters, and for example, unbiased Nusses parameters such as B1, and all of that is measured to 1% or better. Okay, so this gives us some confidence that these formulas really make sense, and like they really work for the real case of a realistic galaxy survey that you're observing, like on the sky. Okay. So let me finish by then saying that, of course, then what you can do is to take the real data, for example, from the BOSS galaxy survey, and try to repeat the same exercise. You can forget about the CMB, like we can just say that the CMB never happened. We can say, let us imagine that the galaxy is all that we measure. Let us use some cosmological model, let's say lambda CDM, and try to fit all the parameters only from the full shape of this galaxy power spectrum monopole and quadrupole. And if you do that, these are the results. So here what is shown in red are the Planck contours, and what is shown, let's say, in blue is one of the iterations. There were several papers with various improvements, but one of these results are similar. So one of these results where you basically get the BOSS measurements. And interestingly, of course, there are some parameters that Planck measures much better. And this is not a surprise because the BOSS volume is relatively small. But some other parameters, such as the Hubble parameter, or let's say omega matter, the error bars in the BOSS analysis, which doesn't have any CMB input, are comparable to the CMB itself. Okay, so this already shows you that currently this large-scale structure data is, of course, inferior to the CMB, but it is not so bad for some things. And in the future, as the observed volumes increase by a lot, we're going to have much better error bars. So I wanted to say a few words about this beyond standard model, but people have been, let me just in one sentence, applying these pipelines to constrain things beyond lambda CDM. And in these examples, adding BOSS data made an important difference. So already we are now able to do things which were unimaginable just a few years ago, where we can measure directly, for example, non-Gaussianities from the Bose data, or constrain some extensions of the early universe and add meaningful information to the CMB using the Bose data. Or let's say constrain ultralight axions. You can see the CMB constraint alone, the Bose constraint alone. In combination, they're much better than the CMB alone, and so on and so forth. So it's an important improvement. And I'll just stop here and show you how the forecast looks like for like a DESI or Euclid-like survey. Here in the dashed line, you have the MOG data for the Planck MOG data, assuming some neutrino mass. And then you can focus on these red contours, which are the power spectrum results, from expected power spectrum results from the DESI or Euclid. And you can see that these ellipses are comparable to Planck. So in that sense, I said at the very beginning that the currently ongoing like large-scale structure surveys will have information comparable to the CMB. But more importantly, in the combination, the two are going to measure things so precisely, much better than each individual one of them. And this is really going to be a big step forward in either really constraining lambda CDM to a sub% precision, or if there is any disagreement or something doesn't work, potentially discovering something new. So I'm now definitively running out of time, and I will just say again in one sentence that there are many things which still have to be done, and the field is now very active. And so for the future, there are various aspects that have to be improved, both in theory and implementation of all these things, and in the data analysis. And I will stop here and take some questions. Yes. Yeah, this is basically like imagine that somebody gives you the underlying density field and tells you you can sample it with a finite number of points. Then if you do a random sampling of the field, you will have a Poisson noise. This is what it is. Now, in some sense, if you want, galaxies do it by themselves, by basically forming just a few of them. They're basically providing us with a noisy field, and we have this sampling noise. Yeah, this is what it is. Now, it's not entirely Poisson because they're not forming randomly. They have to obey some rules. For example, they cannot form in the same place. I mean, they have to there are some corrections to the Poisson noise, but basically it's just very the good approximation, just a constant Poisson noise in the power spectrum. Yes, it is in some sense it's a stochastic background, in the sense that it's exactly what Matthias was saying in the first lecture, that if you have some fluctuation whose amplitude is smaller than this noise, you cannot see it because there can be a random, just by pure chance, this random sampling can conspire to give you some random density field, and you cannot distinguish it from. So yes, like if you have fluctuations with the amplitude smaller than this noise, they're hard to dig out. You have to do some, in the field, of course, you cannot do anything. If you do some summary statistics, like the power spectrum, then you can beat the noise by basically by combining many Fourier modes and so on and so forth, because the noise in each Fourier mode is independent maybe, and things like that. But like, but yes, it's in a sense, this is why I was saying also that in the discussion the first time, that there's this irreducible stochastic background, and if you have some perfect model on very small scales, it doesn't save you because you cannot see it in those small scales. So there is a natural cutoff up to where we can go, and this is up to the point where the power spectrum hits the noise, and after that, the improvement is marginal, or at least much slower, maybe not marginal, but not as good as before. Yes. To the theory, it is very, very easy. So basically, if you want to add the non-Gaussian initial conditions, all that you're saying is that whenever you compute these expectation values, we were always using Gaussian field and Gaussian contractions. Now there will be some non-Gaussian contractions, but those are easy to incorporate. And indeed, for example, this analysis here is done for the, so for example, here, this is done for the non-Gaussian initial conditions. There are already formulas and everything. It is not very difficult to include those. Yes, so let me say that if the ultralight dark matter is 100% of the dark matter, then its mass must be larger than 10 to the minus, I don't know, 19 electron volts or something like that. So those scales are deep inside, it's much more than nonlinear scales. In that case, the dark matter, basically for the cosmological purposes, is the same as normal dark matter. However, if the ultralight dark matter can be a fraction of dark matter, then it can have any mass you want, allowed by the data. So for example, what these people did here is to consider the fraction. You see, like that the axion is a fraction of dark matter. And so, for example, CMB tells you that 2 sigma 15% is allowed. This is the fixed mass, I think 10 to minus 30 electron volts. Then you would see some differences, and you would have to redo the computation of all these EFT, because now you have two fluids. There is a normal dark matter. There will be ultralight axion with the different properties, and you have to do the computation. And so, like, this was not entirely consistently done here, but if you do the leading order thing, then you see that the Bose data, for example, already is better than the CMB by itself. And in combination, you go from, let's say, 15% to 5%. So in the future, we will be able to test any fraction of the dark matter like to better than 1% with this service. And it will be interesting to see if you find something. Thank you.